Welcome to the Shika Serbu Motor channel. This channel provides easy-to-understand explanations of car mechanisms. The content of this video is advancements in ignition systems. As you may know, in gasoline engines, a spark plug ignites the fuel-air mixture by generating sparks. This video explores the evolution of ignition systems used in passenger cars, from the contact point type ignition system to the modern coil-on-plug ignition system. The contents covered in this video are: contact point type ignition systems, distributors, transistorized ignition systems and fully transistorized ignition systems, wasted spark ignition systems and coil-on-plug ignition systems. First, let's take a look at the principle of generating sparks in a spark plug. The ignition system consists of a spark plug, ignition coil, battery, and switch. Inside the ignition coil, there are two coils, the primary coil and the secondary coil. Currently, the switch is turned on, and electricity flows from the battery through the primary coil. The moment the switch is turned off, a large amount of electricity is generated in the primary coil. This effect is called self-induction. The large amount of electricity in the primary coil induces an even larger amount of electricity in the secondary coil. This effect is called mutual induction. The high voltage electricity generated by mutual induction generates sparks in the spark plug. Generally, this voltage reaches anywhere from 12,000 up to 40,000 volts. When the switch is turned on, electricity flows from the battery back through the primary coil. This video will not explain in detail about self-induction and mutual induction. If you are interested, please search for more information on YouTube or elsewhere. Just remember that shutting the electric current of the ignition coil generates sparks in the spark plug. In actual engines, a contact breaker is used to shut the primary coil circuit. A camshaft, which rotates coaxially with the crankshaft, connects and disconnects the contact point to shut the flow of electricity to the primary coil. In this system, sparks are generated not only at the piston top dead center where the air-fuel mixture is ignited, but also at the top dead center during exhaust. In multi-cylinder engines, distributor is used to distribute high-voltage electricity to each spark plug in order to create sparks. The distributor is driven by the camshaft and rotates at half the speed of the engine rotation. A distributor has three functions. The first function is shutting the primary coil electric current in the ignition coil. The cam, which rotates coaxially with the distributor shaft, pushes the contact breaker and disconnects the contact point. In the case of a 4-cylinder engine, the spark plug ignites 4 times per 2 engine rotations. The camshaft rotates at half the engine speed, so the contact points are disconnected 4 times in one camshaft rotation. The second function is distributing the high-voltage electricity generated by single ignition coil to spark plugs of each cylinder. A rotor with a metal plate attached rotates coaxially with the distributor shaft. The high-voltage electricity from the ignition coil is transmitted to one end of the metal plate and distributed to spark plugs of each cylinder from the other end. The alignment of the rotor and contact point of the distributor cap is designed to synchronize with the high-voltage electrical generation. The third function is the ignition timing advance control function. Before explaining distributor operation, let's take a look at what ignition timing advance control is. There are two types of control for ignition timing advance: control based on engine speed and control based on engine load. First, let me explain the ignition timing advance control based on engine speed. This graph shows the relationship between crankshaft rotation angle, cylinder pressure, and ignition timing. Combustion of the air-fuel mixture takes a certain amount of time. When the cylinder pressure reaches its maximum just after the piston reaches top dead center, the spark plug is ignited before the piston reaches top dead center. When the engine speed increases, the crankshaft rotation speed increases, and it is represented by the shortened horizontal axis of the graph. However, since the combustion time of the air-fuel mixture remains the same, the cylinder pressure reaches maximum when the piston has already moved down. It leads to a decrease in engine efficiency. To prevent this, as the engine speed increases, the timing of the spark plug ignition is advanced. The device which adjusts the ignition timing according to the engine speed is called a governor. Two governor weights are attached to the governor base, which rotates coaxially with the distributor shaft. When the governor weights open, it slightly rotates the camshaft base. When the engine speed is low, the governor weights are closed by spring force. However, as the engine speed increases, the centrifugal force overcomes the spring force and opens the governor weights, and it rotates the camshaft base. As a result of this operation, the phase relationship between the camshaft and the contact breaker changes, causing the ignition timing to advance. Next, let me explain the ignition timing advance control based on engine load. Engine load can be expressed as the throttle valve opening angle. When the throttle valve is suddenly opened wide during low engine speeds, the amount of air flowing into the cylinder increases, but the fuel supply cannot keep up, causing a temporarily lean air-fuel mixture. Due to the time it takes lean air-fuel mixtures to combust, the cylinder pressure reaches its maximum during piston descent, which results in insufficient output. To prevent this phenomenon, the ignition timing is advanced. The ignition timing advance control based on engine load is operated by using the negative pressure of the intake manifold. When the engine starts, the throttle valve is closed, and a large negative pressure in the intake manifold is generated. This negative pressure operates the diaphragm to rotate the contact point base in the direction of the engine rotation. This state is the normal ignition timing at idle. When the throttle valve is suddenly opened wide, the negative pressure in the intake manifold decreases, and the contact point base is rotated in the opposite direction of engine rotation. When the contact point base rotates, the phase relationship between the contact breaker and cam changes, causing the ignition timing to advance. Imagine that you drove a 4-cylinder engine car with a contact point for 30 minutes on a highway at 2,000 revolutions per minute. How many times did the contact point repeatedly connect and disconnect during this 30-minute period? Let's do the calculation. The contact point connects and disconnects twice per 1 revolution of the engine. Since the engine speed was 2,000 revolutions per minute, the contact point repeatedly connected and disconnected 4,000 times per minute. Since you drove for 30 minutes, the contact point repeatedly connected and disconnected 120,000 times. If you continue driving this way every day for 1 year, the contact point will connect and disconnect 43,800,000 times. Due to repeating large numbers of connecting and disconnecting, contact point will wear out over extended periods of use. Also, sparks are generated during connect and disconnect, which causes contact surfaces. For this reason, the contact point type requires periodic maintenance. In order to improve this, transistorized ignition systems were introduced to the market in the 1970s. Before explaining the transistorized ignition system, we need to know how a transistor works. A transistor is a type of semiconductor that can control a large amount of electricity using a small amount of electricity. Currently, the transistor is turned off. When the circuit switch is turned on, a small amount of electricity flows into the transistor, and the transistor is turned on. Then, the transistor allows a large amount of electricity to flow, and lights up the lamp. This function is called the switching action of a transistor. The transistorized ignition system incorporates a transistor into the circuit of the contact point ignition system. The transistor controls a large amount of electricity which is applied to the ignition coil circuit, and the contact point controls the transistor with a small amount of electricity for reducing contact point wear or burn. However, since the contact point undergoes millions of repeating connections and disconnections, wear and burn are unavoidable. To further alleviate this, fully transistorized ignition systems were introduced. In a fully transistorized ignition system, a signal generator that detects engine rotation is adopted, instead of a contact point and a cam. The ignite signal that generates the signal generator turns on and off the transistor. Due to no mechanical contact, periodic maintenance of the contact point is no longer necessary. The fully transistorized ignition system has eliminated contact point from gasoline engines. In the 1980s, the EFI, electronic fuel injection systems were introduced, which incorporated various sensors and control unit to manage fuel injection devices. Additionally, ignition timing was electronically controlled using these sensors and control unit. The control unit controls the optimal ignition timing based on signals from sensors such as the throttle position sensor and crankshaft angle sensor. EFI has eliminated mechanical ignition timing control devices, such as governors and diaphragms from gasoline engines. Soon after EFI adoption, the wasted spark injection system was introduced. The wasted spark ignition system integrates two spark plugs for one ignition device. Each spark plug ignites at both the compression top dead center and the exhaust top dead center. With the adoption of this system, it is now possible to distribute high voltage electricity to each spark plug without a distributor, which once caused mechanical and electrical losses. The wasted spark ignition system has eliminated the distributor from gasoline engines. In the mid-1980s, the Coil on-plug ignition system was introduced to the market. This system is equipped with an individual ignition coil for each spark plug, and does not require plug wires that can cause electrical losses. Furthermore, it can control ignition timing individually for each cylinder. The Coil on-plug ignition system has eliminated plug wires from gasoline engines. Today, most gasoline engines are equipped with this system. Thank you for watching. If you enjoyed this video, please consider subscribing to our channel. We'll see you in the next video.